The second, and I guess kind of less frequent, quite frankly, at least what I find in applied work, is that sometimes we actually want to predict the value of a single response of a new value given some value. So again, we're not using the conditional mean to help generate this estimate. All we're doing here is using the regression, but we're calculating the standard errors a little bit differently. Now, why are we doing that? And again, that's because there are two sources of variability in the prediction on a given individual. One is the uncertainty around a group mean, and that's what we talked about before. That is what we used, and we just stopped there. But we need to now consider the variability of an individual response around a group mean, given the fact that we are interested in predicting a new single response from this X naught that we're interested in. Now, to do this in R, it's very simple. All we have to do is change the type of interval prediction that we're using. So here in line 2, rather than interval equals confidence, here we'll do interval equals prediction. Again, I just want the 0.95 confidence intervals. And you can see the point estimate has not changed. That is purposeful. All we're doing is incorporating not only the uncertainty around the group mean, but the individual response around the group mean. And so that's why the confidence intervals are so much greater now. They're much wider, right? Why is that? Again, it's because we're incorporating not only the uncertainty around the group mean, but the individual response around the group mean. Now, when we visualize this, what we'll do is we can actually plot the fitted value, so what we get from a prediction line, then the confidence intervals around that, as well as the predicted values, which I think really helps drive home the point that your prediction values are almost always going to be bigger, if not equal to, your confidence intervals around a predicted value. A major thing that I want to conclude with talking about with regard to prediction intervals and confidence intervals and just fitting a regression line in general is that you want to be very concerned about outliers, and you do not want to extrapolate away from the center of your data. And that is essentially the reason why you want to be worried about outliers, right? They're going to pull your regression line in ways that you may not anticipate, and inherently you're going to have more uncertainty around those areas of the distribution. And again, this is because this is outside the range of the data that you're actually observing. So you're making riskier predictions because you're moving farther away from the X values that you have information about. And there's no guarantee that the relationship is going to hold outside of the range of the sampled X's that you have. Some kind of last things to consider with regard to bivariate regression is that a steeper slope, so having a beta that is farther away from 0, that one doesn't necessarily mean that you have a, quote, stronger linear relationship between X and Y, because we don't necessarily know what the units are. It doesn't necessarily mean that you have like a larger R squared, because you could have a ton of unmodeled variation still in your Y, right? Like X could be a horrible explanatory variable of Y and might have might explain very little variation. And a strong relationship is when the model explains a lot of variation in Y. So when your R squared value is large, that is more likely that you have a stronger relationship because your model in its entirety is doing a better job of explaining variation in whatever trend you're interested in explaining. Having a strong linear relationship will also manifest itself when we look at the fitted predicted values around the fitted line. So if the observations are really close to the predictions, then that means we have a strong linear relationship, right? Like the model is doing a better job of predicting the actual observed behavior. And we know that we can do a better job of predicting the data more generally around the bulk or center of its distribution. And we also know that we can do a better job of predicting a mean rather than predicting an individual value of y, because we have to incorporate in the individual response variability around the given mean, as well as the variability around a given mean. Finally, the inference of these parameters relies on the assumptions of linear regression. And so later we're going to talk about regression diagnostics to make sure that these assumptions hold. To wrap up, today we talked very briefly about making confidence intervals and doing hypothesis tests using correlation coefficients. We also talked about using that type of procedure with estimators and making inferences about parameters. And then finally, we talked about how to make predictions using confidence intervals and prediction intervals. Now, today we only talked about relationships between one explanatory variable and one outcome. Next time, or next module, we're going to talk about how we draw the best line through a hyperspace. And in this instance, we're talking about using multiple covariates.